So I'm really excited to be here. The topic of this talk is going to be two things, which I thought would be really original, but looking at the other talks, I realized maybe have been covered. So I'm going to talk about stream processing, and I'm going to talk about microservices. And I'm actually going to talk about the intersection of these two things. So I think when most people think about stream processing, they probably think about, big data, and it's kind of like you have some MapReduce thing, but faster. And when most people think about microservices, they think about taking a big monolithic application and chopping it up into little pieces and letting people kind of move more agilely. And so intuitively, these things have nothing to do with each other. But I'm going to kind of argue that there is some relationship or some intersection of those circles, and I'm going to try and motivate that and cover that. And my experience in this area came out of time I spent at LinkedIn. So about 2 years ago, I left LinkedIn, but for a big chunk of time, from about 2007 to 2014, I was at LinkedIn. I was one of the lead architects, and I worked on a number of projects there. But two of the big ones were Kafka, and really moving towards kind of a stream-centric architecture, but also the move of LinkedIn from a big monolithic application to like a microservices architecture. So this huge project of cutting up an app while you're hiring more and more engineers. And so over that time, it went from kind of a handful of pieces to something that ran as around 600 services, and from a handful of engineers to several thousand. And this was actually not a pain-free process. There were pros and cons to the microservices. The pro was it actually worked. It did what we had hoped. So we had hoped to be able to basically scale our engineering effort, be able to hire more engineers, and actually make them productive. And think about the marginal productivity of the next engineer. And that was kind of the big interest we had. And with, I would say, a certain amount of pain, we were able to sustain that by doing this. And we got a lot of things wrong in the early generations of this. But the con had to do, really, I think, with operability, with running the big system we'd created. And so we ended up with this call graph. It looks something like this. It was mostly driven by user requests. So you would do something on your app, on your phone. You would do something on a web browser, and that would generate requests to LinkedIn.com, which would in turn fan out to services, which would in turn call other services, which would eventually usually get to some kind of data store. And so this was kind of the architecture for at least the front end or interactive part of the application. And the problem with breaking this into more and more services really had to do with keeping it up and keeping it operational. It's harder to test something if you have to test every possible downstream dependency. What would happen if it got slow? And what would happen if it broke? And that was actually something we spent a fair amount of time on. And it was one of the things that made development most difficult and most different from what we'd been doing in this architecture. And I think one of the things we realized over time was it's actually inherently hard. So if you have 600 services, and let's say 100 of those are in the path of a given request, keeping that consistently fast is going to be hard. Like one of those 100 things is going to be slow roughly every time. And so maintaining a really good 99th percentile, maintaining high uptime, it was hard. And we realized we didn't actually want to have more and more and more services. That was not inherently a good thing in the context of these really, really fast requests. There was a trade-off, right? So the right number of services was not like goes to infinity. And so then we thought, well, what can we do? Like, how can we shrink this? One way to shrink it would be cramming a bunch of stuff together, right? We could say, oh, we'll take all these things that are related and we'll cram them into one big service. But that was kind of the world we came out of, and we knew what the drawback of that was. The drawback was you have a ton of people all coding in the same repository. They don't understand each other's code. They don't know why things work or don't work. So that didn't really solve the problem. And I think what does solve the problem, one of the things we realized was, came out of the fact that we were working with Kafka at the same time. And so one of the ways to get things out of this very latency sensitive request paradigm is to actually make things which are asynchronous. And what do I mean by that? So people use the word asynchronous lots of ways, and they all mean something different. So our service our services were implemented using REST, right? So they were RESTful calls, and they were non-blocking, right? So they were, there were many concurrent calls going on. They weren't blocking a thread. So I don't mean non-blocking when I say asynchronous. By asynchronous, I mean later. Do the work later. If it's possible to take some subgraph of this, take that work and do it later, then it can't interrupt the user experience in any way, right? It can't make the UI less responsive. It can't make it slower. And it turns out that we hadn't really had a great way of doing this. And the question for us was, well, is there a lot of stuff like this? Is there a lot of stuff that we could take and we could kind of push into this asynchronous domain and do it quickly, but not in the context of the user request? Does that exist? And it did for LinkedIn, and I think it actually does for most businesses. So I'll give an example that's not a website. In fact, websites I think are one of the least asynchronous things. I'll give an example which is retail. So I like this example. For a long time I thought it was really overly simplified, but then I think last week Walmart did a blog post and they used this picture, and so I was like, well, if they use this picture, taken from one of our slide decks, I guess it's endorsed. But if you think about how retail works, this could be e-commerce or it could be a big box retailer. It inherently has a lot of parts that are asynchronous. Like when you buy something, that is a synchronous transaction. You give me money, I give you a product, right? Or many products, or I give you a promise that products will ship to you, whatever it is. But there's a whole back end that does things like reordering products, manages inventory in warehouses, adjusts prices, manages shipments and fulfillments. All of that is this kind of big background machine that's churning along and powering the business. How does that stuff run? Is that a REST service? What is it? How do you build it? So I'm gonna be making an argument that stream processing is the way to build this. But let me start with, I think, the technology that came before, the thing that's there. And that's enterprise messaging systems, message queues, whatever you want to call them. And in theory, this actually solves the problem of making something asynchronous, right? You put it in the queue. The queue is really acting as a data store, like a database. It holds the message. And you say, well, I assume it's going to get there because the queue said it had it. It's a reliable store. The processing will eventually happen. It could go to one thing. It could go to many things, right, depending on if it's kind of queuing or pub sub. So this was kind of the traditional solution. We spent a lot of time prior to Kafka messing with different messaging systems, and none of them really worked for what we were trying to do. And they didn't work for what we were trying to do for a bunch of reasons. One was they didn't scale. So if you're thinking of making something the equivalent of your service backbone, and you're gonna have a bunch of services and you're gonna be able to grow your business, you're gonna say, yeah, the whole company is gonna communicate through this thing. You need to have some scalability story around that, right? And message queues mostly don't have a very good one. The second thing is they're really one of the worst storage systems. They're really terrible at storing data. So the core thing they're trying to do, which is provide reliable storage, they kind of fail at, I think, for the most part. Typically replication is not done in the way you would expect of a modern distributed system. They don't provide a lot in the way of guarantees. It's mostly like, well, we write it to the file system and hopefully that worked. And finally, they don't really give you much. Like they give you a message, they store it, but they don't let you do much with it, right? They just hand out messages. And I think this is not surprising. Like if you think about how infrastructure platforms develop, the amount of intelligence and thought that has gone into databases is kind of incredible. Like in every university that has a computer science department, there's probably a subgroup doing research on how to make databases better. And they're churning out papers on how to improve databases. Like there's no university in the world doing research on message queues. I don't even know if the companies that make message queues are doing research on how to make them better. And so this wasn't really a solution for us. And our concept of the problem was a little different. So our idea of how we would do this was we would have what we kind of came to call a streaming platform. So something where we could capture streams of data, and we could use it really for two purposes. One was being able to synchronize data from different data systems. So a kind of backbone for data that was in databases that were backing different services, a way to capture logging data, everything from kind of core transactional stuff to who clicked on what, right? And this would be the way that all these systems could get data, so kind of the data pipelines. But the second use case was around stream processing, right? So that applications could plug into this. They could also react to what happened. And you could build a type of asynchronous service. And so our architecture went from something that looked a little bit like this, where there was a set of request-response things that all talk to each other. These were the REST services I showed on the last slide, but now compressed into one row. And these were mostly in the kind of 1 second, time frame. And there was a bunch of batch things on the bottom that would happen maybe once a day. And we didn't have Kafka at that point, so there was kind of just a mismatch of pipelines between these things, and nothing really truly async. And the kind of replacement architecture that we went to as we rolled out Kafka was this kind of streaming platform in the middle. And it acted to integrate data systems, it acted to integrate applications, and it was the thing that powered these type of asynchronous but near real-time apps. And that kind of future near real-time app, I think that's stream processing. And so I'm gonna bring that out. This way of building asynchronous services, that to me is stream processing. So I'm gonna give kind of an introduction to what I mean, because I want to shake people out of the mindset that stream processing is like, faster MapReduce, that's what it should be. A lot of things have been built that are kind of that, but I don't think that's really the use case. So let me say what I mean. So, I think a good way to, cut up computer programs, to categorize them, is by how they get their input and how they give their output. So, the most common thing that most people spend time building is request-response programs. This is like REST services, HTTP, OLTP databases. You give it a request, you get a response. Most people also have some experience with batch processing. This is if you make a command line program in your intro to programming class, it's probably a batch process. It reads in a file, it outputs a file. Stuff that happens on data warehouse tables or Hadoop clusters, that's kind of batch processing. It's always a little surprising it still exists, but it does. And let me use these two things to kind of really motivate stream processing. So if you think about request response, what it kind of really is you're giving one input, the request, and you're getting back one output. So for every input, there's an output. And the inputs and outputs, the inputs kind of come independently of each other usually, and they kind of fail independently. But another interesting thing about this, which is almost weird to say, is that request response processing, if you build a service, it only processes future requests. So what do I mean by that? I mean, like, you don't process past requests. You start your service, and any request that comes in the future, you process it. And that's how messaging systems work, and that's how this type of request response processing works. Batch processing is actually the opposite. So batch processing, you kind of read all your inputs, and you kind of churn through it, and you produce all your outputs all at once, right? So instead of one input, one output, it's kind of read the whole file, output the whole file. Maybe you don't read the whole file at once, but still the same idea. In batch processing, it's not about future inputs, it's about all the past, right? So inherently, a batch program only processes data that's been stored. It processes the stuff already in the table, the stuff that's already in the file. And stream processing is basically, the way I'm thinking about it, is really just a generalization of these two things. So I want to be able to take, not just one input goes to one output, though I could do that, and not just a bunch of inputs go to a bunch of outputs, but anything in between those. So I can take some inputs and produce some output, and some more inputs and produce some output, and I'll have control over that. And furthermore, this stream of inputs, it'll be never ending. Like, it'll just continue, because now I have control over when output happens. And this will generalize both this idea of processing the past, because if my stream is stored, I can go process it, data from the past, but it will just keep processing into the future. So it's a little bit like if you're running a data warehouse query or something, and it computes results on the table that's there, but when it gets to the end of the table, instead of stopping, it just keeps evolving as your data changes. So what I don't mean is something that's necessarily transient or approximate or lossy. That's not what I mean by stream processing. I just mean something that is fast and flexible in that way. And so if I come back to my retail example, I think you can kind of see a retail operation as being inherently something that happens on streams of data. It's like not an unnatural way to think about it. It's actually more natural than thinking about it as a big batch process, right? So you have a stream of sales, which is input. You have a stream of product shipments. You're making inventory adjustments as these products arrive or are sold to maintain your inventory on hand. You're maybe making decisions about adjusting your price. You're doing, analytics on that. You're reordering new things. Those are all in reaction to what's happening, in reaction to this stream of events that are occurring. And this is a little outside of the domain of what people normally think of stream processing for, where they would think of it for, I don't know, click streams or something. You can absolutely have streams of clicks, and that's probably very important to a e-commerce retailer. But this is something that can also be applied to kind of core logic about your business. So now let me come to Kafka and how stream processing works with Kafka. So Kafka is really built to be the center of this picture, the thing that you could unify different data streams with, unify different event streams from applications, and the foundation for doing processing on top of those streams. The data model in Kafka is really simple. So I think a lot of people are familiar with it, but I'll give kind of a 30-second intro just to set up how we do stream processing. So the data model is a stream of records, and you can call them events or messages. People are pretty sloppy with the terminology. But each record is just a timestamp and a key and a value. And Kafka doesn't enforce a data model, so you can have any format of data for the key or value. Kafka just treats it like a byte array. And these messages or records are organized into a log. So a log is just a sequence of records all in a row. So I don't necessarily mean like an application log or an error log. I mean more like a database commit log. Right? So each record is appended to this log. It's given a unique number called the offset, and you can have many readers that read this log. And this turns out to be actually a pretty good basis for publish-subscribe messaging. This isn't how traditional messaging systems work, but it actually works quite well. If you read kind of a distributed systems textbook and you want to read about how to implement reliable broadcast, it's going to be something like make a log. And so if we call that writer a producer and we call the readers consumers, then we have pub-sub messaging where the readers are subscribing to changes in this log. And this turns out to be really important for stream processing. So I talked about stream processing as kind of being a generalization of batch processing. Well, this log is basically kind of the manifestation of a stream. Like if I say stream, that's kind of a very fuzzy word. I don't really know what it means. I hear a lot about it, but what is a stream actually? But a log is a concrete thing, right? It has this, it has a form, you can reason about it. So this in Kafka at least is the manifestation, the data structure of a stream. And it allows you to treat data that has already occurred, data in the past that has already been appended to the log, the same as data that will be appended, because you have this kind of linearization of everything that will happen. So you could imagine doing batch processing on one of these logs, right? If I start at the beginning, run to the end, and then stop and produce output, that's a batch process. But instead of stopping, I can also keep processing and keep reading as data arrives and is appended. And this is particularly useful, this log concept. It shows up already in the world kind of with databases where you're replicating updates. This is called change data capture. And you might call this log of changes a change log. So you can think of replicating the updates to a database and applying them on replica databases. So this is kind of like bin log replication in MySQL or Golden Gate for Oracle. These are similar. Kafka is basically doing this, but it's much more open as a platform. So you can have all different types of data systems that would replicate these changes. And I'll come back to why this is important as I start to talk more about stream processing. So the core data structure in Kafka is a topic, which is just a stream or feed, which is made up of these partitioned logs. And that's done to be able to scale out the capacity and spread that stream over servers in the cluster. And Kafka has 4 APIs. 4 core APIs. So it has a producer, which appends data, like writes data, sends the stream. It has a consumer, which reads the stream. It has a connector API, which allows you to build integrations to existing data systems. And it has a streams API, which does stream processing or transformations. I'm going to focus on this 4th API. The other 3 are super interesting, but this is a stream processing talk, so I'm going to talk mostly about this. In this picture, this is how you build those streaming applications, how you build the stream processors. I'm using streaming app and stream processor interchangeably. And so this API, we added it roughly in the last year. We've actually been toying with this idea since we started Kafka. The first prototype for this was actually before Kafka was even open source. That kind of became a processing framework in its own right, which we maintain separately, and then we've kind of really done it for real now. And our motivation in doing this was really the following. So before we had this Streams API, there's really two ways you could do stream processing with Kafka. The first one I would call hipster stream processing. So, I think the idea with a hipster is you like things to be simple. So you like a bike that has no gears, or this guy's laptop is, I think, a typewriter. You're kind of getting back to basics. And so, doing that with Kafka is actually really easy. You can do stream processing just by reading streams of data using a consumer, transforming them in your app, and writing back derived results. And so what's wrong with that? That's actually so simple compared to stream processing things you would hear about. Why not do that? Well, it's actually a pretty good solution. I mean, it's really easy to reason about. You kind of own your own app. You can write it however you want. But there are some hard parts when it comes to stream processing. So there are some hard problems. So reasoning about how you're scaling out, reasoning about what happens when your application fails, maintaining any kind of state. So if I'm just processing one input and producing one output, that's easy. But if I'm counting many inputs together, that becomes more complicated. I have to maintain state that persists in between messages. Everything having to do with time. And then finally, what happens if I need to change my code and kind of go back and recreate the results? These are all kind of the hard problems in stream processing. And if you kind of do it from scratch, you kind of have to solve these hard problems. So it's a little bit like the typewriter. It's pretty good as a laptop until you need to backspace, which occasionally happens, not to me, but. So the other approach that's been out there is different stream processing frameworks, and these work as kind of an independent entity that you can deploy your program into that will consume data from Kafka and produce output. And these are actually quite good. I think there's been a whole sequence of these. Maybe Storm was one of the earlier ones. Samza was an early one that we built at LinkedIn. Spark and Flink, I think, are popular and more powerful. And I think our motivation in adding stream processing directly into Kafka was really kind of that working with these frameworks, while they're powerful, they were often really complicated. So the kind of architecture for a lot of these frameworks would end up having a lot of moving pieces. So you would have Kafka, you would have some kind of stream processing framework like Storm that you would set up. If you wanted to do any kind of stateful processing, you would probably need a database to maintain that state in that would be external. You would have to deploy your code into that. You would output to some kind of database, and maybe your final app would query that. And then if you want to be able to reprocess or rerun and everything, you need some batch system that will reprocess. This is kind of like the Lambda architecture. And so you might have a whole separate setup for recomputing past results when you need to do that in backfill. And so, if I'm imagining my past life where I have all these moving pieces in our big microservices architecture, I'm thinking, oh yeah, I want to simplify my world by moving stuff async. I'm basically not going to spawn out one of these for simple services. I'm not going to be able to run that. I'm not going to be able to operate it. It's basically just too complicated. So I think the real challenge for this whole stream processing area is making this stuff simpler, making it simple yet still powerful. And that was our motivation for the Streams API in Kafka. And what we wanted to do was really maintain this architecture, but give you a modern, kind of fully featured stream processing capability. So make it so that your app is just an app. It's like any other app, but give you a, fault-tolerant, distributed, fully featured, stateful stream processing capability. So the key operations for the Streams API, instead of just read and write, you basically have a bunch of ways of transforming streams. And so you can map, filter, aggregate, or join. This, the nature of this API is a lot like the Streams API in Java or the Collections API in Scala. if you've seen those, or many of the reactive APIs that let you give some kind of fluent set of transformations on streams. How is this different in Kafka Streams? Well, it's fully distributed. So in other words, when you are talking about an aggregation, you're talking about that kind of in a way that distributes out across a cluster of machines, potentially across many instances of the application. It also fully understands the semantics of Kafka, so when is data processed and when is it not. So that's what's different. So these operations, there's a bunch of variants of these in the API, but they do kind of what you would expect. So map is going to take an input stream, and it's going to transform it into an output stream. Filter is going to filter out rows. Aggregate is going to do kind of counts and sums and other ways of combining rows. Join is going to join. So what does it mean to join? Well, you can join two streams. So if I have a stream of clicks and I have a stream of impressions, what was shown, I can join them together to figure out which impression led to a click. But actually more interesting is I can join things to tables. So I can join a set of customer events to the customer account information, right, and get the kind of full details of the customer for each thing they did, right? And so a lot of the, I'll talk more about this, but a lot of the operations in Kafka Streams can apply both to a pure stream as well as to a table. And a Kafka Streams program, it's a Java API. It looks something like this. It's Java, so it's short, but not that short. It's going to have some config at the top. You kind of tell it your serializers, and then you have your transformation logic. Fundamentally, this is just a main method, right? It's just a Java main method. There's like literally no magic here. You choose how this program starts and stops. All we will do is handle the fault tolerance amongst the running instances of the program. So if I zoom into that logic, this is the transformation. That program was doing a word count because all like big data things are required to count words because it apparently is a very important problem. This is a streaming word count. So whereas normally you would have a bunch of documents and you would count the words in the documents, this is going to give a running count, right? So for each word, it's going to say, okay, now the count for the word the is 1,375. Now it's 1,378, right? And it will do that as new events arrive. And so I talked a little bit about how this compares to other kind of reactive things, right? So is this reactive? Yeah, kind of. I mean, it's not implementing like the reactive streams API, but I guess it conforms to some, the things in the reactive manifesto. But really, this is aimed at the asynchronous domain. This is processing things which are persistent to that log already, which I think makes it very different than trying to build services, which are going to respond back with an answer. And the result of this, is you get a fairly simple program, but it actually does kind of everything you would expect of a modern stream processing system with no additional moving parts. So, it's a simple library. It gives you sophisticated windowing. It allows you to reprocess data. It doesn't do micro-batching, and if you know what that is, I'm sorry. It maintains state as you compute it. And I'm going to go through a few of the areas. Like, I can't go through every aspect of Kafka Streams just because of time, but I'll go through a few areas where we tried to make things simpler. So I said that the primary project in this area was to make stream processing simple enough that it could be a mainstream application development methodology, that you could go and build a service, with like one person and deploy it and have it work and not need 14 moving distributed parts. So the first simplification is this just uses Kafka to do all the things Kafka does. So it inherits the same data model. It uses offsets to keep track of what is processed and not processed, so you have a clear picture of what has been consumed. It uses Kafka as the mechanism to deal with back pressure. It uses Kafka's group management facility to do the kind of partitioning and fault tolerance among processing. It uses Kafka's changelog capability to maintain state. And this has a lot of advantages. So the first advantage is if I update my code and I want to rerun it to reproduce results, I just kind of rewind it back in time and reprocess the log. And that's actually, I think, a very easy way to reason about what you need to do when you reprocess. Much easier than like trying to glue on a Hadoop cluster for back processing data. It does require you to keep more stuff in Kafka, but it's a lot easier to do. Secondly, this naturally inherits the timestamp that we added to Kafka's data model so that you can do windowing based on kind of the event time of the messages, so that you can count messages based on when they actually happened in the world, not when they arrived at the Kafka cluster or when they arrived at your stream processor. So the second simplification has to do with just getting rid of the stream processing cluster. So it's kind of an unusual thing, right? If you use any of these stream processing frameworks, you deploy your application into the processing framework. It's a little bit like the world, if for those who remember it, of your kind of application server, where it's like you have to go put the program into the app server. I think it's a somewhat uncomfortable way to manage your program. And I think getting rid of it is actually a lot easier. And this is an advantage, I think, of our approach. Basically, the Streams API, it's just an API to Kafka. It's a library. It goes with your program. And you can kind of manage your program in any way you want, right? So you control how your program starts. You control how it's configured. You control how it's packaged up. And that means it works with kind of anything on the deployment coolness spectrum. So whether you are kind of R-syncing your code out to servers and starting it via SSH, or if you're kind of running it in Kubernetes with containers and whatever, either of those are fine. Obviously, if you're running it in something elastic like Mesos or Kubernetes, you're going to be able to scale out your processing job elastically and shrink it as you want. If you're doing it with rsync, maybe it's a little bit less elastic, although, I don't know, I guess you could rsync pretty elastically if you want to. But the key point is, however you do that for the applications you have, it will work with Kafka Streams. You don't have to learn about Yarn or something to learn how to deploy applications because they are doing stream processing. So the third simplification is actually one of the deeper ones, and it's one I can only just touch on in the time I have, but it has to do with combining the concept of tables with streams. So this is a little bit of a mind-bending one, but to motivate it, let me say why you would want to do this. So in this example I gave, the retail example, there's clearly a set of things which are naturally streams of events, right? Sales kind of feel that way to me, like a sale occurred. It's an event, it's immutable, it happened at a point in time. A shipment arrived, it's an event, it occurred, it's immutable. But there are things that I'm maintaining here which are basically tables. So my inventory on hand, how many of a particular product do I have? Well, that's clearly being updated by the event. When a sale occurs, probably some product goes away. But it's a table, it's mutable, it gets updated, it changes. So how can you kind of combine events in the world, things that are happening, with the state of the world? Like the event changes the state of the world, and it turns out that there's a really interesting relationship between these two that comes out of these change logs that I described. So as state changes, we can basically log that out, which produces a series of events, right? The current, the current number of products on hand is this. The current number is this. That's an event. That event can be then applied elsewhere. And this is how Kafka lets you manage tables and interact with tables by turning them into a different type of stream and giving you semantics to process tables. And this is actually quite powerful. So what do I mean by this? I mean you can take streams of data as they come out of data systems, and you can process that stream and create a derived view of the data. So in databases, this is what you would call a materialized view, right? But it's a materialized view that can happen across many databases, totally different, disparate data systems, and can also plug in streams of events that come from apps and have no data system at all. So an example of this that people talk about a lot is something called a customer 360 or unified customer view, where you have basically bits of data about your customer spread over many databases in different parts of the business, different business units or whatever. They all keep track of something, and you want to stitch it together into some kind of unified view. That's a materialized view. It happens over many different data systems, maybe in different data centers. That's an example where this ability to do processing on tables is really powerful. And this is actually integrated throughout. So when you are doing a count in the Streams API, the output of that is basically a table of your counts. That table actually flows out as a stream, a changelog. Other things can process it and use it as well. So there's this really interesting duality between tables and streams. I can't get into it in too much detail just because we only have so much time. But I think it's a really fascinating thing. It's something we've kind of fully integrated in a way I haven't seen elsewhere, so that you can do this type of materialization. And we've actually taken that kind of as far as you can go. So you can take the output of a streams job, which would just go to a Kafka topic, and you can put it in a database in its own right. But you can also query it directly. So you can build an application which uses the Streams API, and it is keeping a count, maybe, in one of these tables. And you can actually query your app and get that current count. So it actually allows you to combine that kind of request response, like interactive querying, with this background processing, stream processing that's computing it. So you can both compute the materialized view in your app and query it. And each of these materialized views is basically kind of like an event-sourced store. So it's keeping data in the app of what has been computed, but it's also keeping the log of changes that led to that in Kafka. That's kind of the persistent version of it. So I won't get too deep into that because it's kind of an interesting area. This feature of being able to do the interactive queries is coming up in the next release in a few weeks. If you're interested, I think we did a blog post about this a few weeks ago on the Confluent blog, so you can check it out. And this Streams API, of course, it works also with the Connect API. So I mentioned this briefly. I didn't really say what it was, but Kafka has a Connect API that allows you to run connectors to existing data systems. So if people write these connectors, you can write them yourself, but a lot of times there's one that already exists. So if you want to pull data out of a MySQL database, you probably don't need to write a connector for that. There's a pre-existing one that will use the MySQL changelog or query via JWC. If you want to load data into HDFS, you don't need to build that integration yourself. There's something that already exists. And so this combination of Connect and Streams, you can kind of think of it as being, if you come out of the data warehouse world, a little bit like a real-time version of ETL, right? So for those who don't know, ETL is kind of extract, transform, and load. So for any kind of data pipeline usage, that makes sense even if you're doing it in real time. The extracting and loading is clearly Connect, which is plugging into different destination systems, different stores. The transforming is Streams. The difference here is, of course, that everything is kind of purely real time. And so that's how those pieces fit together in this streaming platform vision. This is kind of what we set out to build with Kafka. It's gotten adopted in really thousands of companies now at very large scale. And the company I co-founded, Confluent, we basically produce a distribution of Kafka that tries to package up a lot of the things you would need as an open source platform to get started with it. So this has facilities to make RESTful calls into Kafka. It has connectors to a bunch of data systems. It has management tools that let you kind of operate it. And it has a facility for managing schemas or data format to ensure compatibility across different systems that interact with Kafka, which is particularly important because if you can broadcast out data to many apps, then when that data changes, you don't want to broadcast out breaking things to many apps. Okay, so that's the extent of my talk. I think I have a couple minutes left. So I'll take any questions that people have.
The K-tables in the new version you guys released.
Yep.
Does that allow it to transfer RDBs to Spark?
Yeah, I mean, there's no direct integration between K-tables and Spark, except that it is in Kafka. And so Spark streaming can hook up to Kafka. And so you can use any of those stream processing frameworks like Flink, Spark, the Kafka Streams API. They all kind of can integrate around Kafka. And so it is actually possible to use more than one for different use cases. Other question?
Separate this RD stream processing. Is it another point of failure in Kafka?
Yeah, okay, so the question is, how separate are the streams? Is it another point of failure? Can you say how you mean? Let me speculate on what you mean, and you tell me if I'm right. Let's say somebody writes a really bad stream processing app that uses a lot of memory. Can I crash the Kafka cluster? No. The processing is happening in your app. It is not happening in the Kafka cluster. There is no way for the stream processing to crash the Kafka cluster. From the point of view of the Kafka cluster, you're consuming streams and you're producing streams, but the same as any app would. So we have in Kafka facilities for throttling or quoting the amount of reads and writes you get, and that would manage the capacity a streams job can use just as it would any other application or thing that connected to the cluster. So yeah, you can absolutely run out of memory and crash your streams app by doing something silly, but you can't crash the Kafka cluster. Question?
You mentioned 4 core APIs, producer, connector, and streams. Have you guys implemented any of the first-class APIs into the Kafka workloads or streams?
Yeah, so there's definitely support for that. So we, over the last year, the question is, I said there was 4 APIs. To what extent does that have a presence on the Kafka cluster, and to what extent is it just a, Java API? Yeah, so over the last year, we basically reworked a little bit about the data model to integrate time, and we reworked the way that we handled groups for fault tolerance, and that work was primarily motivated to make it possible to manage a group of streams apps and make them fault tolerant, as well as manage a group of connectors, as well as manage a group of consumers. Previously, we'd done that all through Zookeeper, and it wasn't generalizable at all. And so in that respect, yeah, it's totally part, that part is part of the protocol. The actual implementation of like filter is just totally, in the library. Right now, there is only a JVM, library for this. So you can do it in Scala, you can do it in Java, but we haven't ported that over for streams. We haven't ported that over to other languages yet. Other questions? Yeah, I think that's super interesting. So the question is, what about SQL support? I think that's super interesting. It makes a ton of sense to want to run, SQL. They're not really queries; they're more like SQL transformations on streams of data. So we haven't done that yet, but I think it's super appealing. Question in the back.
So Kafka kind of by design pushes a lot of responsibility for delivering semantics to the client, and that ends up with people using workarounds of various degrees of complexity. Do you think it's important long term to take on more of that responsibility, whether that's in the broker, the client, in the producer, or do you feel like that makes sense for it to remain kind of for developers to work around?
Yeah, so the question, just to repeat, is Kafka, leaves a lot of the semantic responsibilities on the developer. To what extent should Kafka take over more of that? Yeah, there's a couple answers to that. So there's work that's going on right now on strengthening the semantics in Kafka in a couple ways. So one is making writes idempotent, so that if you write and you get back like a network error and you don't know whether that write occurred or not, you can retry safely. That's really important. So right now, nothing that does like stream processing on top of Kafka can give you like correct output if it doesn't do some kind of internal deduplication, which basically nothing does, because of this ability to get duplicate writes. The second is the ability to do consuming, processing, and outputting like transactionally. So those two features I think are super important, and there's kind of interest in work, and we should have a design proposal out for that relatively soon. And that will give you kind of exact semantics across connect, Kafka, the cluster, and streams in the presence of failure. So what you want to be true is if one of the instances of my app crashes, a broker crashes, a client crashes, I can guarantee that I will get the same output as I would otherwise. People sometimes call this exactly once delivery, which is like super misleading and doesn't really mean much, but it's not necessarily exactly once delivery because, of course, whoever is at the very end, when they consume, they have to be cognizant of the fact that if they fail and reread a message, they're rereading it. But all that processing upstream can be solved in the system. So that was kind of a confusing answer. I don't know if it, I think the short answer is yes. One last question. Anybody? No? All right.
So in the stream
Yeah, so the question is basically how does like concurrency and parallelism, how does that work in this model? So obviously you can get parallelism by starting more instances of your app, and that will be parallel because it's a different process. But it also allows you to control the number of threads within one of those processes. The reason to do that is just there's some overhead for a JVM. So like you're probably better off with one JVM with 4 threads rather than 4 JVMs, just because it adds up if you're going to have a lot of cores and a lot of those. The model for processing is actually extremely simple. It's basically just kind of an event loop that grabs, processes, produces output, and so on. So for each of those threads, they're kind of extremely simple and deterministic in what they do, which is actually, I think, one of the great strengths of the model. But yeah, you can specify a number of threads, which will give you more parallelism within within the process, and that's effectively almost identical to starting a separate process, but you'll reuse all that JVM space. All right, super happy to talk with people afterwards. I'll be around for a bit. Thank you so much.